We are, okay, you saw my announcement that we don't have homework due tonight.
Yes, sir.
Because it turned out, I thought I had questions like about temperature scales and stuff, and I don't have any of those available. So those were what I was going to give you. We'll get to these after we go over the bottom four. Here's your test, Judith. The bottom four of the test questions. So let's get into this. The question that had the worst outcome. Question number 13. What is the absolute pressure at the bottom of a 12-foot, which is 3.66 meters, deep swimming pool filled with water? I didn't look at the distribution of answers, but I expect that the problem is that people did gauge pressure instead of absolute pressure. Because you have the equation delta P is equal to rho GH. And so that's going to be the pressure at the bottom minus pressure atmosphere equals rho GH. So pressure at the bottom is equal to pressure atmosphere plus rho GH. And then you just put in your numbers. It's like 13.7, and then it's like 190 or 210 or something like that. But we only have 3 sig figs. So that was how that one went. That was the worst problem on the entire test. Which actually, after I got to looking at the grades and everything, I felt much better about the test than I did in class on Wednesday. In fact, the majority of you did the best on the synthesis section, which, since that's the one I value the most, made me feel good. We did poorly, though, on the knowledge section. The next 3 lowest scoring questions were in the knowledge section. Notice the lowest one was in application, the next 3 were in knowledge. The synthesis were pretty good. So what condition is necessary for any momentum about an axis to be conserved, such as when Andy was spinning on the chair? Andy apparently was a sore point for y'all, because the 2 questions with Andy in them were 2 of the bottom 4. Welcome back, Andy. I am so happy she's here. So, just like with linear momentum, it comes down to Newton's second law. The rotational equivalent for Newton's second law is that the net torque is I alpha. And so about the axis of interest, and then we can avoid that guy getting upset at me if I take off the vectors and I just say the net torque about the vertical axis is equal to I about the vertical axis. Alpha Z, oops, that's a Z, not alpha. And so, this is absolutely correct, but that's also equal to change in angular momentum over change in time. They're the same equation, just like in Newton's second law, 2 different ways of writing it. So for angular momentum to be conserved, that means delta L, the change in angular momentum, is 0. And so if the change in angular momentum is 0, what does that require? The net torque has to be 0. So in this case, we were doing the Z direction. So the net torque about the Z direction is equal to change in angular momentum about the Z direction over change in time. And so that was the condition. The net torque about the axis. And you might recall when I talked about this, I noted that her angular momentum was only conserved in this direction. If she leaned to the side, that wasn't conserved because the chair would provide a counter torque to keep her from falling over. Next one. Which conditions, select all that are correct, below guarantee equilibrium for a non-rotating system? I think I overemphasized this so much that people got the nuance and forgot the broader part. Because I think everybody answered B as one of their answers. B being a constant velocity. Because that's what I emphasize. Constant velocity is equilibrium. But there are 2 answers up here that are constant velocity. Not C. C is constant speed.
I knew that, but I just didn't see select all that are correct. So like, I just chose the one that I thought you would think that was thought.
I thought that you thought that I thought.
Exactly.
But if you have constant speed, don't you have constant velocity and then zero acceleration?
I thought you were going to work with me. Wait, but I thought that you thought that I thought. Okay.
But I thought that I thought that speed was just
It's just speed, no
the
direction.
scalar quantity of the velocity.
So,
Right, but it doesn't have direction, so you can have an acceleration by changing direction with constant speed. Yeah, so the most common answer was only answering B. The second most common answer was answering B, C, and D. And the reason C is not correct is because you could have a change in direction and still have a constant speed. Okay, the final one that people did poorly on. As Andy rides her bicycle to school, traveling forward, of course, what direction is the angular momentum of her rear tire pointing? And so we talked about this in class. If she's going forward, the tire's rotating like this. How do you determine the direction of the angular velocity and therefore angular momentum?
Your right hand.
Your right hand. You wrap your fingers the direction that it's rotating. Your thumb points the direction of the angular velocity and angular momentum. So it's to the left. All right. Those were the questions that people scored the worst on. And effectively, I took those out of the grade. I say effectively because I graded out of 9 instead of out of 100. If you add them up, that was actually, it would be 89 points remaining if I took those ones out. So that's effectively what I did. Any questions about the test, the grading? No questions? Okay, well, while you're reviewing to see if you have questions, let me go real quick to the Moodle page for the class. And this should now be available. For the last couple of years, Lisa Keene has been working with me to try to improve the class. And so we did this last year. We're doing again a survey to get your opinions on how the class is going, what things could be improved, and that kind of thing. So it ends with 3 open-ended questions where you can mention anything. You know, we highlight things that we think could be problematic. The questionnaire it's fully anonymous. It will collect email addresses to give us a list of who has responded, but won't correlate their response with what they answered. So it is fully anonymous. I want to make sure you understand, your email address is collected, because I always get really annoyed when it's completely anonymous. What division do you work in? What major do you teach in? Well, there's one of me. So it doesn't have identification like that. So please fill this out over the weekend, not on Sabbath, of course, because, well, we're using it to try to improve the class. All right, back to thermal expansion. Last class period, we introduced this, but we didn't have time to do the problem. So we're going to do the problem, and then we're going to talk about calorimetry, and then you're going to do a problem calorimetry. Yeah. So here are some coefficients of thermal expansion. Notice it has coefficient of linear expansion, coefficient of volumetric expansion. So if we have a solid like, gold has a linear expansion of 17 times 10 to the minus 6. That times 10 to the minus 6 is kind of important. Per degree Celsius. It says per degree Celsius. What else could it have said and still been the same number? Per kelvins. Technically, we don't say degrees with Kelvin, but per kelvins. So when you read that, you don't have to use Celsius. You don't have to use Kelvin. You could use either one because it's a change in temperature. So gold is times 10 to the minus 6. So it's going to increase by 17 millionths of its length if you increase its temperature by 1 degree Celsius. Not a very big amount, right? But it does grow. And you saw this here was using brass. I shouldn't leave these in water. It's just dumb of me. But if we look at brass there, brass is just about the same, 19. So change of temperature of 1 degree Celsius, it would increase in size by 19 millionths. Well, how much did I change the temperature when I put it in this flame? I changed it by many hundreds of degrees Celsius. And so many hundreds of degrees Celsius makes the percentage much bigger, big enough that, this it's easy to pass through wouldn't pass through. The volumes, remember I said the coefficient of volumetric expansion is 3 times the linear for most situations. As long as it's what we say isotropic, same in all directions, it's 3 times. So if you look at the top one, 25 times 3 is 75. 19 times 3 would have been 57. That's off by 1. 17, you can see that there's some slight variation, but essentially this number is 3 times this number. Liquids, there is no linear expansion to liquids because the liquid is a bulk material. So we only have its volumetric expansion. All right. With all of this said, we're going to do a problem. Ready? Yeah. Yes, you are. And why did it not go forward? Because it hates me. That's right. So here's our problem. Suppose your 60 liter, which is 15.9 gallons, steel gasoline tank is full of gas. So both the tank and gasoline have a temperature of 15 degrees Celsius. Okay, so was probably not the right word there. How much gasoline has spilled by the time they warm to 35 degrees Celsius? Anytime we're solving a problem, we need to identify what kind of problem it is. In classroom problems, it's usually pretty straightforward because we're talking about a certain topic. But this here, when it asks how much gasoline is spilled, how is that going to lead you to knowing what type of problem it is?
This is a change in volume problem.
Okay, so we're going to have something with change in volume if we have some spill. And so then with changing volume, it says it changed temperature. That tells us, hey, this must be a problem with thermal expansion. Now I'm going to change application so I can write better. One minute. So I'm going to write down now, I've got a picture here. I'm not going to redraw a picture. The things I know, volume initial is equal to 60.0 liters. Temperature initial is equal to 15.0 degrees Celsius. Temperature final is equal to 35.0 degrees Celsius. Those are the numbers given in the problem. But then I know 2 additional details. What are the 2 additional details I know? They're extremely important details. Without them, you cannot solve the problem.
You know that you're working with gasoline.
Yes, I know that I have material 1 equals gasoline.
And I guess material 2 would be steel gas tank.
So that means I'm going to have K1. Actually, you know what I'm going to look at? I'm not going to look at K. K. Sorry, I'm thinking about the wrong thing anyway. It would have been alpha. Beta 1 and beta 2. Why am I looking for betas rather than alphas?
Because it's volume.
Because it's volume I'm looking at. With the gasoline, it's a liquid as well, so the liquid's only going to have a beta listed. The steel should have both, so I just look back at my table here, and I have, steel, iron or steel, beta's 35.
What degrees is that? Like, what
Excuse me?
degree is that?
Up here? Is that what you're asking about?
Like, I can't read it.
It's degree C, and for some reason the degree is underlined. I couldn't figure out why and did spend the time to. Okay, then for fluids we have, you know what? Gases is not gasoline, just to be clear. Petrol. So for gasoline, 950 units of times 10 to the minus 6 per degree Celsius. And for iron steel, 35. Okay, I got to make sure I wrote those right. 950, not 960. See, that's why you check. So there I have my betas. Now I have to devise a plan. How am I going to determine how much gasoline spills? Find both the change in volumes.
And then figure out how much volume, how much excess gas you have versus how much excess.
Okay, I find the change in volumes, and now I can find my total volume by adding my initial volume to that. But if the gasoline's change in volume is bigger, the excess, in other words, the difference in the change in volumes will be how much I spill. And so my strategy concept is thermal expansion. So my equation, delta V is equal to V initial beta delta T, beta because of volume. That's a comparison, COMPAR. And then delta volume gas minus delta volume for steel is equal to the volume spilled. So now I just have to put numbers in. Go ahead.
What is that? V delta spilled? Oh, V spilled.
Yeah, V spilled.
Okay, sorry.
So now I just put the equation in. For gas, it's V0 beta 1 delta T. For the steel, it's V0 beta 2 delta T. I hate putting extra numbers in the calculator, so I factor out what I can. And now I put in my numbers, 60.0 liters times my change in temperature, which is 35.0 degrees Celsius minus 15.0 degrees Celsius. And then beta 1 and then I have to calculate that. Now, somebody have a calculator to calculate that for us? Thank you. While people are punching in numbers, let me point out something that you may not have noticed. Some places I put degrees Celsius, and one place I put Celsius degrees. I should have put Celsius degrees up in the left-hand column there where you see the thermal expansion coefficients. The table didn't have it that way either. That's why I wrote the way the table did. But there actually is a difference between degrees Celsius and Celsius degrees. It's a technicality. No one's going to hit you for doing it wrong. I'm not going to grade you on a test for doing it wrong. But if it says Celsius degrees, it's actually talking about changing temperature. If it says degrees Celsius, it's actually talking about temperature, if you're going to be technical. So I had a textbook that says, I'm trying to think of exactly how it's, it said 5 Celsius degrees equals 9 Fahrenheit degrees. It's like, no, they're not even close. But it was talking about changes. A change in 5 degrees Celsius is the same as a change in 9 degrees Fahrenheit. Or Fahrenheit degrees. See, I just changed it around in order as I said it. Okay, what do we get for the answer?
About 1.098 liters.
Really that big?
Yeah.
Okay, that's a lot of gas to spill, right?
I mean, out of 60 liters, is it really?
Well, out of 60 liters, that's still, I mean, yeah, it's 1/60th. So that makes it, what, 1.7%? That's a fair amount. So when you fill your gas up, of course, I always say, ooh, I want to go fill my tank on a cold day.
Oh, I heard about that, yeah.
Because then I'm actually getting more molecules per gallon, right? But the thing is, those tanks are down on the ground and it's distributed at a fixed temperature. So you're really not getting that savings. But as soon as you put it in your car tank, if it's cold outside, it's going to start shrinking. Yes.
Why do we care about the gas tank?
Well,
Why
because-
don't we just care about the gas itself?
Well, because the vessel is also going to grow. The gas tank grows as well as the gas. The gas tank doesn't grow nearly as much as the gas, but it also grows. So if we just calculate the increase in volume for the gas, it would have been bigger than this 1.098 liters by a small amount. So I guess to be correct, as correct as we can under under the approximations we make in a general physics class. Approximations we make, well, I'll talk about those approximations for thermodynamics in just a moment. So did my battery go dead or what? It's no longer advancing. I'm sad. Water is not normal. Water has this special property that we call breaks your pipes when it freezes. Why does water break your pipes when it freezes? I heard a word expansion. But what are we talking about there when we say expansion?
When it freezes, the molecules expand.
When it freezes, the space in between the molecules expands. So the density drops when it freezes. Now, if we go back to everything we've been talking about, the differences between solid, liquid, and gas phase, solid, they have fixed positions. As you raise the temperature, they're bouncing off each other harder, which makes them move farther apart and expand. And so how could this be? That doesn't match that story. It's what?
The lines change that the crystals.
It's because of the hydrogen bonds. Hydrogen bonds? Well, yes. It's the bonds that form Van der Waals bonds between oxygen in one water molecule and hydrogen in another. You have oxygen being more electronegative. It's pulling the electrons toward the oxygen, and hence the hydrogens appear to have a positive 0.35 charge because their electrons spend less time with them. I said hydrogens there, didn't I? Yeah. The oxygen has like a minus 0.7 charge because it's getting extra time with the electrons. And so then you have a dipole-dipole force, essentially, that makes hydrogens from one molecule attracted to oxygens from another. And that force is a structure that actually makes it expand. So ice, being a Van der Waals solid, expands when it freezes. Is there something I'm saying wrong?
No.
No,
Okay.
it's an explanation for like the hydrogen stuff.
Right.
Okay. So that's why it expands when it freezes. But it's not just that. Water is the most dense at, 3.98, if you want to be all kinds of technical, degrees Celsius. That's where it's the most dense. And that's where it's 1 gram per centimeter cubed. If you get hotter than that, it does exactly what you expect. It expands when you heat it up. But if you cool it from 3.98 degrees Celsius, it also expands because it's starting to align. So water is kind of unique. The ice being less dense means that ice floats on water. And that's super important. What would life on Earth be like if ice didn't float on water? Our drinks. Yeah. What we would have would be a cold popsicle world. Because what happens now when it gets cold? You have ice that forms where the cold air meets the water. And that ice stays and floats on the top, forming an insulating barrier so that you slowly freeze down and you only get so deep and it stops. Because you have heat coming up from the earth, and when you get the ice thick enough, the rate at which cold air is cooling, drawing heat out, is the same speed as which the earth is replenishing it. And so you have liquid water in your lakes year round, unless they're really shallow lake. But if it didn't work that way, when it gets really cold, the ice on top would freeze and it would sink to the bottom, right? If the frozen ice was more dense, and then the ice on top would freeze and sink down. And it would just keep freezing until your lakes were frozen solid. And then the frozen solid lakes, well, you've lost a lot more heat, and you're going to have the earth cool down. What was that? There would also be no ice fishing. That is a correct. That was very sad. Okay, it went backward. Now, okay, so I just had to hold long enough for it to remember how to work. Calorimetry. You guys know this term? So calorimetry is studying how heat makes temperatures change. And the heat capacity, which we virtually never use in physics, is defined as the heat per change in temperature. So if I have this amount of water, and I put 10, what are the units of energy? Joules. So if I put 10 joules of energy in here, its temperature is going to go up some amount. And if I just measure that ratio, that tells me the heat capacity. This one here has a slightly different amount of water, so it's going to have a slightly different heat capacity. But they're both water. So we usually don't talk about the heat capacity, we talk about the specific heat capacity. What does it mean when I put in specific? It means I'm talking per unit something. And if it doesn't have any qualifier like volumetric or constant volume or constant pressure, then it's per unit mass, or well, actually molars is the other one. So we usually talk about the specific heat capacity, or we'll sometimes drop the word capacity, just say specific heat. And the specific heat is the heat divided by mass, change in temperature. And that gives us something that is constant for any material that's the same. So like all water has the same specific heat, C. Doesn't have the same heat capacity. It has the same specific heat. And so if I have water and I put some amount of heat Q in, the change in temperature is going to be that heat added over MC. And if I remove heat, what's going to happen to the temperature? It decreases. Now, a little historical note. 3 more slides and then problem. Historical note. Back in the day, when physicists were kind of learning about heat, back before 1900, when physicists thought they knew all of physics, were they embarrassed? The theory was that heat was some kind of fluid. It was something that flowed. Remember, we do say heat flows a lot, right? And so their theory actually had 2 fluids that flowed. There was the caloric, which would make things hotter when it flowed, and there was the frigidic, which would make things colder when it flowed. And so people worked with this caloric and frigidic, these 2 fluids. But of course, as physicists, you're trying to figure out what's going on. You try to make measurements, and I don't know why I can't remember people's names, but somebody was drilling cannons, boring them out.
Oh, the whole, okay.
And he knew, of course, you have to put copious amounts of water on there to cool the cannon as you're boring it out. And then he's like, wait a minute. I am putting energy in joules, and I'm producing heat, which they measured in calories. So a calorie was the unit used to measure how much caloric you have. And like, maybe heat is just a form of energy. Remember, I introduced it as an energy transfer. And so then we had, was William Prescott Joule? I don't know. I can't remember anyone's names today. But Joule did an experiment where he stirred a container of water and measured the temperature change. And by measuring how much work he put in to stir it and measuring the change in temperature, he was able to come up with an equivalence between heat and work. And so we have the calorie, the unit for heat, which we still use in America because you know what we use in America? Dumb units. So 1 calorie is 4.186 joules. Now, of course, what would the calorie have come from? The calorie is actually defined as the amount of heat necessary to raise 1 gram of pure water from 14.5 degrees Celsius to 15.5 degrees Celsius. That's the definition of a calorie. And now, some of you probably already knew the definition, but I said it a little different. It's not technically to raise a mass of 1 gram by 1 degree Celsius, because it turns out the specific heat of water varies with temperature. For this class, we will assume it to be constant. So for this class, we could say the definition is just 1 calorie is the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. But the true definition is 14.5 to 15.5. That number 4.186, I have no idea why the world can't agree on certain things. 4.186 is what all physicists, in their textbooks at least, agree is the relationship between a calorie and a joule. But a lot of biology books say 4.184. I mean, it's not a big difference. I don't know why we can't agree. So, a calorie is a unit of heat. A joule is also a unit of heat. Let's say that I decide to go on a diet. I mean, why would I? It's pretty obvious. If I go on a diet, I count calories. I've just been talking about calories as a unit for heat. Is there a relationship? Okay, Judith says yes. What's the relationship, Judith?
I'm pretty sure, like, as you put in, calories into your body, like, it's the energy that you use to, like, do work in general. So.
Okay, the calories we're counting are energy that we're bringing in. But a dietary calorie is written with a capital C, and a dietary calorie is 1,000 calories, or 1 kilocalorie. Okay, so that's confusing, right? So if you're counting calories, you're counting the energy in the food that you're consuming in kilocalories. How do they get the energy of the food in kilocalories then?
Well, burn it.
Yeah. The same thing you do with witches. Oh, I'm sorry. That's a Monty Python sketch. What do you do with witches?
Burn!
You burn them! You burn them! I'm sorry.
Please.
No, we will not. That would be wholly inappropriate. So they burn it. They make what's called a bomb calorimeter. And what you have is a very strong chamber that you fill with, you put in very carefully measured amount of whatever you're trying to do. Like, we have her Nature Valley Crunchy Oats and Dark Chocolate. If instead of taking the specific ingredients in the already calculated value, we just wanted to know, we would take this bar and say, okay, this bar is 16 grams, cut it down to a smaller piece of cake. Here's a representative 1 gram. Put it in my bomb calorimeter, fill it with pure oxygen, put a little filament in there, because it only takes a spark to get a fire going. Seal it up, put it in a bucket of water, and then we carefully measure the temperature of that water, and we put a little current through that little filament so it catches fire inside and whoosh, burns, right? Because it's 100% oxygen, very oxidizing environment. Anything that can burn will burn. And then we measure how much heat was released by how much the temperature of the water increased. Which makes me then say, so wood, how many calories is in wood? Our body can't metabolize those calories though, right? There's definitely calories you would measure with that bomb calorimeter, but you can't metabolize. Judith.
Eat bamboo, though.
In my Chinese food?
Asian.
Yes, because they can metabolize it. All right. So here's some typical specific heats. By typical, I mean typical materials. Aluminium That's how you pronounce it if you were in a British country. They also spell it differently to match. So aluminum, 900 joules per kilogram degree Celsius. The degree Celsius is in the denominator. It's kind of hard to tell the way it's printed here. Or 0.215 kilocalories per kilogram degree Celsius. So the two units we have here are joules versus kilocalories. Remember that 4.186 relationship between a joule and calorie. So if I take my 0.215 and multiply it by 418.6, I should get the 900. So either number, you can quickly translate between one and the other. They're both shown just for convenience. So let's look for water. Water is a liquid. Here's water. And we can do the calculation real quick. 1 times 4.186, I think I put the decimal in the wrong place when I said it before. It's 4.186 times 1,000, 4.186. It is 4.186. That is a big number compared to everything else in that whole table. That's really significant, once again, for life on Earth. Because water has a big specific heat, if I put heat into water, how does its temperature change compared to if I, for instance, put it into, let's see, do we have silica here? Don't have silica, so I'll go to the next best thing of concrete. If I put that heat into concrete rather than water, how would the change in temperatures compare? And I'm going to write the equation just for people as they're thinking. Q is equal to MC delta T. So delta T is equal to Q over MC. So water having between 4 and 5 times the specific heat, how does the change in temperature of water compare with the change in temperature if I put it into concrete?
The water would be slower to change than the concrete.
Okay, now slower is a time word, but it would change less. The water would change like 1/4 to 1/5 as much. That's an important thing. That means water will stabilize the temperature much more than other things. So you guys know I'm from California, the coastal region of California. You didn't know that? Yeah, I grew up in Monterey Bay. So we have this ocean water. That ocean water comes down from Alaska. So if it comes down from Alaska, it's kind of cold. And the sun shines on it, what happens to the temperature of the water? Increases, but not very much. And then the sun goes away for the day. What happens to the temperature of the water? It decreases, but not very much. So that water keeps the temperature really stable. Where I grew up, the coldest it ever got was like sometimes in the 40s, but usually it didn't get below 55. The hottest it ever got, sometimes into the 80s, but usually it didn't get up above 80. Very small band of temperatures, because we had that water right next door that buffers the temperatures. So if you live next to water, it helps to keep the temperatures from swinging wildly. Now here in Nebraska, you know what we're next to? Not water. We have basically silicate, which concrete's a good approximate for. And so we're going to have much bigger changes in temperature with sunlight and whatnot. So we have bigger swings in temperature than what we would have if we were coastal. In fact, we're pretty much the same latitude as where I grew up. And of course here it gets much below 55 typically. And it gets much above 80 typically, because we're not close to a big body of water. Yeah.
So do you think global warming is partly due to the humanization and like putting concrete everywhere? Like
That's a very big question. The building cities makes a very significant local impact on the temperature. And so you probably have read about, depending on which side of the conversation you're on, the government adjusting data because of the heat island effect, or the government fudging the data to make it match their narrative, their agenda, depending on which side of the aisle you're on. But we know that it has an effect. And so that's the reason for a justification of fudging the numbers, making the numbers different than they really are, because they're trying to account for that effect. Okay, so water has two properties that are really important to us. One is, in terms of climate, one is that it floats when it freezes, and second is that it has a high specific heat, so it keeps temperatures from fluctuating wildly. By the way, water has a much better effect on the west coast than it does on the east coast in terms of temperature, because the winds blow from water to land, typically on the west coast, and from land to water on the east coast. So if the winds are blowing from water over to land, the water makes a much bigger effect on your local climate. Here, it just comes straight down from the north or straight up from the Gulf. They meet, and we have happy times when they meet because, yeah. So moving on, let's do, well, we have to talk about changing phase before we do our problem. Oh my goodness, look at the time. Changing phase. When you change phase, in theory, if you're going from solid to liquid, you put in more energy and you give a molecule enough energy to break free of its fixed location. And so the energy didn't make the molecule move faster, it made it break free. So if you're at the melting temperature and you put more heat in, instead of making the molecules move faster, you made them break free, you made it change phase. So the temperature stays the same as you change phase from solid to liquid. And then if you get up to the evaporation point, you have the same thing. You put in heat and it changes phase at the constant temperature. Now I say this in theory because how many people have taken organic chemistry? In organic chemistry, did you not do experiments where you measured the melting or freezing, and you measured the temperature as melting or freezing, you saw the temperature change as it was going on? Oh, you did GChem. Okay. So you have that experience. Why is that violating what I just said? It has to do with purity. If it's perfectly pure, it actually would have done what I said. The more impure it is, the more the temperature is going to change while it's changing phase, because you'll have some parts effectively melt at this temperature and some melt at this temperature, and you have a range of melting temperatures because of the impurities. So for our physics class, we say it's perfectly pure, has a fixed melting temperature, a fixed boiling temperature, and while it's melting, it'll stay at that temperature. Now, for lab next week, I'm not going to be here because of any surgery, but you're going to have part of the lab is measuring cooling and freezing water, and we'll be plotting the temperature as it does that, so we'll be able to see how accurate that is for our water. So as you put in heat, if you're at the melting temperature, it changes phase rather than changing temperature, so we don't have the Q equals MC delta T. We have Q equals ML, where M is the mass that changed phase. Now it's the mass that changed phase. If I start with a cube of ice and half of it melts, that M would be the half that melted. It wouldn't be the entire cube because it didn't all melt. And L is what we call the latent heat. Now you have two latent heats, the latent heat of fusion and of vaporization. So melting, freezing is called the latent heat of fusion. I swear I have that written on here somewhere. I know it's on the next slide. And evaporation, condensation is the latent heat of vaporization. Doesn't matter if you're melting or freezing, it's the same latent heat for the transition. And it depends on your material, so the latent heat of fusion for water is different than the latent heat of fusion for steel. So here's a table showing typical latent heats. So, and you guys have taken chemistry and you know about polar molecules and non-polar molecules. It makes a difference on the melting points and the freezing points, or melting and freezing. And vaporization, melting and freezing would be the same points. But anyway, you can look here and you can see a bunch of materials, and it has the melting points, the boiling points, and the latent heats of fusion and vaporization. Once again, in kilojoules per kilogram or kilocalories per kilogram. Just putting both for convenience. So let's look at water again. Water, yep. 0 degrees Celsius is its freezing temperature. And it's 334 kilojoules per kilogram. Compare that to other materials, high or low. High again. There's a lot of heat that is necessary to melt ice. Now, Sarah brought up global warming or climate change, and you have all kinds of different measurements. One measurement that I consider pretty important is measuring the temperature in the upper atmosphere, because that's not going to be affected by humans. That's just going to be something to tell us about the globe. And that hasn't changed much at all. And so, of course, people, and I happen to be one of these people, who think that man is not very responsible for the change, that we have a whole lot of other things like the time when the Earth is closest to the sun, which is right now early January, the tilt of the Earth, those kinds of things play into climate change more than anything you or I do, but that's my view. That hasn't changed much. But I have to admit, it's not going to change much as long as we have frozen ice year-round on Earth. Because that frozen ice, it takes a lot of heat just to change the phase of the ice. So as you have more and more heat coming in, you melt ice, the temperature stays roughly the same. But when the ice is gone, you put in that same amount of heat, now the temperature is going to go up. So if you're worried about global warming, when all the ice is gone, the rate of temperature change will accelerate dramatically because of all that heat that's necessary. Now let's go on further and look over here. The latent heat of vaporization, once again, huge number for water. That's why we throw water on fires. You throw the water on the fire, first it has to go from roughly 20 degrees Celsius to the boiling point of water, which is 100 degrees Celsius. So you have that 80 degrees Celsius with the fairly large specific heat. A lot of heat necessary just to raise temperature. But then you have an enormous amount of energy necessary to change it into steam. So it's just taking a huge amount of heat away from the fire, taking away one leg of the triangle of fire, which I'm sure I said wrong before, the triangle of fire. Fuel, oxidizer, and heat. That's the triangle. You take out any one of those legs, the fire goes out. Part of your theory you have to take in fire academy. It doesn't go very deep. So, how do we solve calorimetry problems? I am going to give you homework with calorimetry problem. The method, which obviously we're not going to do in 2 minutes, is reasonably straightforward. Identify each item and write an equation for heat. If you're in one phase and you're changing temperature, you're putting in heat while it doesn't change temperature, then you have Q equals MC delta T. While changing phase, Q equals ML. Now my preference is to always make change in temperature, temperature final minus temperature initial. I don't have Q is equal to MC absolute value change in temperature. I have Q equals MC temperature final minus temperature initial. And then I add up all of the heats. And if I have an isolated system, thermally isolated so I can have no heat flowing in or out of my system, it has to change between things, I add up those heats and they come to 0. So here's the problem we were going to do. An ice cube of mass ice is 100 grams. At temperature of ice is minus 5 degrees Celsius, is dropped into an insulated cup. Insulated, so we're going to have the sum of Q equals 0. That is containing water at 350 grams of water at 20 degrees Celsius. What's the final temperature of the ice and water is the question. Interim questions to help you along the way. Does the ice fully melt? Obviously, you have to do a calculation. You can't just say yes or no. How would you determine if the ice fully melts? If it doesn't fully melt, what's the final temperature going to be?
0 degrees.
Probably 0. If you have a mixture of ice and water, it's going to be the melting temperature. So what you'd want to do is say, okay, how much heat is it going to have to pull out of the cup to lower that temperature to 0. And if I put all of that heat into my ice, will it fully melt? So that's the first thing you have to answer to determine, does it fully melt or not? Now, if I'm doing this problem, you know what I do? I assume it fully melts, and if I get a nonsense answer at the end, then I go back and redo it saying, oh, I was wrong, it doesn't fully melt. Second question, how many heat equations do I need? I have ice cube that warms up. What's it going to do after it warms up a little? Melt. What's it going to do after it melts? Heat up. So I need Q for ice heating. I need Q for ice melting. Then I need Q for melted ice heating. That's just the ice. Then there's the water. So finally I have Q for the water cooling. Now I need equations for each of these. So it's the mass of the ice, specific heat of ice. Changing temperature for the ice. What's the final temperature for the ice? 0. We know that because that's the temperature where it changes phase. So there's my temperature for the ice heating. For the ice melting, mass of the ice times latent heat of fusion for ice. And then for the melted ice heating, mass of ice C of water, because it's melted now, times temperature final minus 0, because the melted ice started at 0. And then finally, mass of water, C of water, temperature final minus temperature initial water. I have those 4 things now. I add them up, and what do they have to add up to? They have to add up to 0. And so that's how you would solve. You know all of the numbers in there. You look up the C's, you look up the L, and the only thing you don't know is temperature final. All right. Have a happy Sabbath. Thank you. Remember, please fill out that survey.